I don't know.
Okay, in order to spot the plate, you want to get a little bit of your dye in your tiny little pipette here. You want to place it on your spot card, and hopefully you spaced it evenly so that they won't mix. You just want to put a small dot on your plate.
That's why I came around and said, okay,
and that'll be fine.
Plate goes in.
Next, you want to take your plate,
that way you know
place it face down in your beaker like this.
That's probably okay, but I can't say that.
Take your solvent, squirt it on the back of the plate.
You don't need to dry it.
Where it just touches the bottom of your plate. And then wait for the plate to pick up the solvent and pull the dyes up. And then you want to take your values and see where the dyes are and work your equation to see your reference values.
And then you take, for spotting the plate, first we need to draw a line a centimeter above the bottom of the plate, and then we distribute those spots for each spot of the die, and then we draw some of the die up here, and we will put this along the line, and we only need tiny drops, tiny spots of the die. So here it goes, and then this is the spots for all the dies. And after we do this, we put the plate face down, a large enough beaker, and then we add the solvent from the back of the plate. Solvent should be below the line of the pencil draw line on the plate.
It's kind of funny though.
So we put our solvent in the beaker. We need to cover the beaker with. We use this microcapillary in order to draw some of our dyes. Now we're going to apply our plate. Gently, we're going to do it in order to get a small spot.
We got to the spot. It's like 30 seconds just to pour the solvent in.
Now, we're going to turn in our plate face down on this beaker. Then, we're going to add our solvent. Mine is a classic acetic acid. We're going to add the solvent to the back of the plate, to the plastic side. Just have to make sure that it's not going to exceed our pencil line. We're going to have to cover our beaker with a piece of plastic wrap.
Okay, now you must make sure that you remove your plate before the solvent goes over the top, absorbs over the top of the plate. Now the reason for this is in our calculations of the retention factor. Okay, in order to calculate your retention factor, you must know where the solvent front ended, in other words, where it stopped on your plate, which I've indicated right here. You must know where your dyes started on the line. Usually you want to draw the line and start them all in the same spot, which this line's right here. Next, you want to measure your distance from the line where your dyes started to the line where your solvent ended. This is your solvent travel. In this particular instance, it's 66.8 millimeters. Next, you want to measure from about the middle of where your dye stopped, from there to where it started. This is your dye travel. This particular dye is 22.1. Now you want, in order to get the retention factor, you divide the distance your dye traveled by the distance of solvent traveled. So it'd be 22.1 millimeters divided by 66.8 millimeters, and this would be the retention factor of this particular dye. Now I've recorded this in my book. This is the distance that the dye traveled, which in this instance, since I've marked it as 1 on the plate and 1 here, is bromocresol green. The distance it traveled was 22.1 millimeters, and then the distance the solvent traveled was 66.8 millimeters, which equals a retention factor of 0.331 millimeters.
So we get our plate out from the beaker before that solvent front goes over the top of the plate, because if it goes over the top of the plate, we wouldn't be able to measure the distance the solvent traveled. And then we get it out and we circle each of the spots here, and we measure the distance the solvent traveled and the distance of each of those spots traveled. And then we can record our data on our notebook like this. And first we need a reference guide to every spot we put on the plate, and then we calculate the RF value of each spot. And by doing that, we divide the distance of the spots traveled by the distance the solvent traveled, and we get RF value for each of these spots.
We have removed our plate from the beaker, and we drew a line in order to show how far our solvent has traveled. And then we draw the line, and the distance between these two lines will show the exact distance. We circle each spot that we have in here, and then we measure the distance, which shows how far each one of our spots have traveled. Then, in order to measure the retention factor, we need to divide the distance of each one of our spots by the distance that the solvent has traveled. And we divide these two together, and then we can find the retention factor.
Chromatography is useful because it helps to separate and determine the substances in a given mixture. This is done by dispensing a mixture between a stationary phase and a mobile phase. When the fluid or the mixture is dispensed between these mobile and stationary phases, the molecules that react strongly with the stationary phase will slow down and tend to stay slow. Substances in the mixture that react weakly or less strongly with the stationary phase will move quickly and tend to move along with the mobile phase. This is to say that likes kind of dissolve likes. Substances with high polarities will move with other substances of high polarities, and substances with low polarities will tend to stay with other substances of low polarities. In our experiment, we used TLC plates. Now the plates had low polarity, and we also used solvents. The solvents had high polarity. So the dyes we put on the plates, if they had high polarity, they tended to move along with the solvent. As the solvent went up the plate, the dyes tended to move up the plate with the solvent. If they had low polarity, if the dyes had low polarity, they tended to stay towards the bottom of the plate and stay with our stationary phase, which is the TLC, again, the TLC plate. Now, substances, different dyes on the TLC plate. Now, if comparing substance, one dye to another dye on the same plate, let's say substance B since substance B has moved further along the plate, then its polarity is more similar to the solvent that we used with this plate than substance A, which didn't move quite as far. Which means this polarity is more similar to the TLC plate's polarity, which is low. And we used 3 different plates and 3 different solvents. And certain dyes say this was dye A and this was dye A, just on different plates. When comparing the 2 plates, if the substance, say it's dye A, moved further along the plate on one plate than the other plate, so it moved further along on this plate than to this plate, then the solvent we used on this plate, say this was water, this was acetone, then substance A, or dye A, had a more similar polarity to water than it did to acetone.